second video. Yesterday, I took you through what we are going to be talking about throughout the program. And I mentioned a lot of things. Yes. So today specifically, we are going to talk about the refrigeration cycle of the system. As you remember, there are a number of elements that work together to make the system function. And the very first one is the refrigeration cycle. By refrigeration cycle, as you hear the word cycle, it means that it is something like in a loop. It is continuously moving around. It is a cycle. Yes. So there is a compressor in the mix, a condenser, coil, valve, expansion valve, and evaporator coil. So these all also work hand in hand to make our systems function. The very first one is the compressor. The compressor is like the heart of the system, yes? The heart of the system, as you hear the word compressor, meaning it is compressing something. In this case, it is compressing our refrigerant. The refrigerant is the fluid. I won't call it a liquid because it is going to be in two states. It can either be a liquid or gas at some extent throughout the cycle. So it is a fluid that is going to be moving around the system to make sure that our intended desire, cooling or heating is achieved. So this compressor is going to be compressing that refrigerant and then pushing it around the system, just like the heart pumps around the blood around your body. The next component after the compressor is the condenser coil. For the condenser coil, this is going to be removing heat from the refrigerant and dispersing it to the environment. Then from there, the refrigerant will continue and come to the expansion valve. The expansion valve now, what it will do is to drop pressure. The compressor was raising pressure and pumping the refrigerant around. Now the function of the expansion valve is the opposite of the compressor. Now this one is going to increase the volume of the refrigerant, and then the refrigerant will proceed the evaporator. Now the evaporator is the coil or the heat exchanger that is going to be inside our rooms, cool the air, or this is the coil that will be inside the refrigerator to cool the food stuff. Yes, so from there, after cooling our air, the refrigerant continues. Now it has picked up heat, it continues around the cycle, go back to the compressor where the process started from, and then it will again start over again, and continuously the process continues until we achieve what we desire, until the temperatures in the rooms come down to our set point. So that is the brief explanation of this cycle. So if you to understand it better, let us first look at the second slide. This one is talking about the relationship between volume, pressure, and the temperature of fluids in general. For a closed system, it is illustrated in the figure above that the volume is inversely proportional to both pressure and temperature, and that the two are directly proportional to one another as shown by the arrows. So the volume in a closed system, the volume of a fluid is inversely proportional to both pressure and temperature. Yes, as we can see with these arrows, volume, if volume goes down, temperature will rise, as you can see, by the indication of this arrow direction. When volume falls down, pressure increases. Then when volume falls down, sorry, here it was temperature. So when volume falls down, pressure increases, and when volume falls down, temperature increases. And the reverse is true. When the volume increases, the pressure falls down. The same thing to temperature. When you increase volume, temperature will fall down. Then down here, we can see the relationship between P and T, pressure and temperature. When pressure increases, temperature also increases. And when temperature reduces, also pressure has to fall down. That is by the indication of the arrow. So you need to understand this relationship if you're to go on with our refrigeration systems or refrigeration cycle. If you don't understand this, you have to get this concept that volume increases as temperature and pressure fall down, and volume reduces as pressure and temperature increase. That is the relationship. And then pressure and temperature are all moving together. They move in the same direction. When pressure increases, temperature increases. When pressure reduces, temperature also reduces. Now, this part explains what happens. Yes, that part of volume and pressure explains what happens at the compressor and the expansion valve. At the compressor, as we said, it is compressing, so it is reducing the volume. It is reducing the volume of the refrigerant. So when we reduce volume of the refrigerant, what happens to pressure? Pressure shoots up, it goes up. And the same thing applies to temperature. Yes. So when we compress our refrigerant, we reduce volume, and temperature and pressure increase. That's why even this line out of the compressor is known as the hot gas line. Hot is very hot and at a very high pressure. The refrigerant exits the compressor at a very high pressure and very high temperature. Then the same theory here at the expansion valve. Now at the expansion valve, this is going to be the vice versa, the opposite of the compressor. The compressor increases pressure. Now the opposite is reducing pressure reducing pressure by increasing volume. So this expansion valve is going to expand the refrigerant. Is going to expand the refrigerant. So it expands it in terms of volume. Yes. So refrigerant flows into the expansion valve in a tiny tube. Then it flow out in a divergent manner. So that's why this is termed as the expansion valve. It expands the what? The refrigerant. So that is explained by our second, explained by the second slide. So secondly, so when the volume of the refrigerant is reduced, both its pressure and temperature will increase, and the reverse is true. Secondly, from the second law of thermodynamics, heat travels from regions of high concentration to regions of low concentration. Secondly, from the second law of thermodynamics, heat travels from regions of high concentration to regions of low concentration. Yes, so this means that heat will leave regions where it is of a high concentration to go to regions where it is of a low concentration. So hot goes to cold. You understand? Hot goes to cold. Just like when you put a metal bar and you stick it in fire, the end that is in fire is going to heat up, and then that heat will transfer through the rod up to your hand through the process of conduction. That's a process of conduction, but it's a form of transfer of heat, but it explains that heat is going to travel from where it is very hot to the side that is cold. Okay. So that second statement explains what happens. It explains what happens at the coils, the condenser coil and the evaporator coil. Yes. So as we said, the compressor will increase the temperature. That's what we are picking out. The compressor will increase the temperature. Now, as the refrigerant flows into the condenser, it is going to be very hot. When it comes into the condenser, remember the condenser is a unit that is going to be outside our houses or outside our conditioned space. So this coil is going to be dissipating heat. It will be giving off heat. The air, when you bring cold air and pass it through this coil, it will collect heat and go with it. Let's see. Okay, so now this is what happens in the coils. This is a tube. This is a tube section, a cut section. So I've cut through the tube, and you can see what is happening inside. So inside the tube is our refrigerant. And on top of this tube, on the outside of the tube, is where the air is going to be blowing. So this coil here is like these are copper tubes, very many copper tubes that are bound together, but with some kind of holes or perforations through them. Not perforations like the tube has holes. No, it doesn't have holes, but it is made in a way, in a spaghetti way, that it will be having some spaces in between the coils, the pipes. Yes, so spaces in between the pipes will allow air to flow through. So this diagram shows us a section of that pipe and a section of the pipe interacting with air. So what is on the inside of the pipe is the refrigerant, and outside the refrigerant, outside the pipe is the air. I'll go back to the first, the condenser coil. At the condenser coil, refrigerant is coming into these pipes. These are like pipes all put together. So the refrigerant is flowing into these pipes, very hot. Now the air outside, the ambient air outside, surrounding that coil is cooler compared to that refrigerant. I'll give an example of refrigerant coming into this coil at around the 100 degrees Celsius. It flows into these pipes at 100 degrees Celsius. It's just a random figure. Then the air outside, maybe it is around 60 degrees Celsius, I would say. Like for instance, here in the desert, sometimes it is 50 degrees Celsius. So the refrigerant is 100 and the air is 50 degrees. By the law of the second law of thermodynamics, which states that heat travels from regions of high concentration to regions of low concentration. This indicates that the refrigerant that has 100 degrees and air that has 50 degrees, heat will travel through the pipes, through the pipe, as we can see, through the walls of the pipe. Heat will travel through those pipes and come into air. So the 100 degrees refrigerant going through the pipe will give up its heat through the pipe, and the air around the pipe will blow away that heat and go with it. So the air is coming in at 50 degrees Celsius, but after going through the coil, its temperature will rise, maybe up to 100, up to 50, up to 70%, up to 70 degrees, sorry. So the refrigerant will lose heat in that sense. Maybe it comes to around 60, and maybe the air that is leaving will go at around 70 or 75. So the essence here is that heat is going to move from the refrigerant and go into the air. So the refrigerant that will be coming out of this coil will be cooler compared to what came in. And then the air that will be going through the coil will come out hotter compared to how it came in. Then, when we go to the evaporator, this is the unit, this is the coil that is going to be inside our rooms. Inside our rooms, we want to remove heat. Maybe our temperature is around maybe 30 degrees Celsius in the room, and then we want to remove that heat. So the refrigerant now, we say that when it goes through the expansion valve will increase its volume and reduce its pressure and temperature, lowering pressure and temperature. Now, when it lowers the temperature, it will lower the temperature to an extent that it is cooler than the temperature inside our rooms. Maybe the refrigerant now is coming in at 20 degrees Celsius. Remember, our room is, the air in the room is hot at 30 degrees Celsius, and then the refrigerant is coming in as 20 degrees Celsius. So when we blow air through this coil, this hot air through the coil, the heat will travel from the hot air into the cooler refrigerant that is going through the pipes. The same theory that heat is going to travel from hot to cold. So now the air is coming in hot and giving up its heat into the refrigerant that is cooler. Then the refrigerant will proceed as at a higher degree compared to how it came in, and then the air will come out of the coil cooler compared to how it came in. So it's just the opposite. The evaporator is just the opposite as the condenser, and then the compressor is just the opposite of the expansion valve. If you understand these two statements, if you understand the relationship between volume, pressure, and temperature in closed systems, and then the theory of the second law of thermodynamics of heat from hot to cold, if you understand these two statements very well, then it's like you have understood 50% of the course. If you understand it very well and you can explain it to anyone, then you have understood 50% of what is involved in the program. Because that's what we are going to be dealing with. Always, that's what we are dealing with. We want to remove heat from the food. We bring in cold refrigerant and pick that heat. We make sure that the refrigerant we are bringing into the unit is very cold compared to the temperatures in the space. If the refrigerant is cooler, it will pick up heat by force and take it out. Then when we take refrigerant outside into the environment, if the environment, the air around, or the ambient air around the condenser coil is cooler than the refrigerant coming to that outside unit. If the refrigerant is hotter and the air is cooler, it will leave the refrigerant and go into the air. That's it. Then we go to manipulating volume. If we manipulate volume, we increase volume or reduce volume, we can play around with temperature and pressure. You understand? So if you understand those two statements very well, then you're good to go. This diagram is a further explanation of the refrigeration cycle. Yes, this is now another type of evaporator, a coil. This is supposed to be inside our rooms. Then the expansion valve or metering device. Then this is the distribution line that is going to be expansion line, leaving the expansion valve into the coil. Then the compressor here, discharging. I said this is the hot gas line, or otherwise called a discharge line. So it is discharging into the condenser. Now through the condenser, it will give up heat and then proceed. So these colors, the red and blue, indicate red indicates hot and blue indicates cold, of course. So the pipes are color coded such that you can understand that in this section of the unit, the refrigerant is hot or warm. Then in this section of the unit, the refrigerant is cold. Then this one you have understood. As you can see, refrigerant. So this is thermal energy transfers through the tube walls. Next is talking about the refrigerant, the blood that is moving around. Now we need to understand this blood move. What are refrigerants? A refrigerant is a substance used in the refrigeration cycle to transfer heat from conditioned spaces that desired disposal point. A refrigerant is the substance used in the refrigeration cycle to transfer heat from where it is not wanted, where we can dissipate it freely. Yes, so from inside our rooms to the outside. As discussed before, this refrigerant flows through the cycle and keeps on changing phases from liquid to vapor and then back to a liquid as it absorbs and releases heat. Now, I don't know how many of you have ever heard of latent heat. Latent heat, during my high school, I studied latent heat in detail. This heat, this is a type of heat that is hidden, like you can't measure it using our normal thermometers. So it is hidden energy, yes. But this is what makes the change of a substance from one state to another possible. Yes, it will change, this type of heat will change a liquid into a gas, or that type of heat is going to be lost by a substance, come from a gas into a liquid. So at the condenser, there will happen latent heat of condensation. At the condenser, to be latent heat of condensation, this is whereby the refrigerant is going to condense from a hot gas into a cool, I would say warm refrigerant. It's warm, just warm, because it is not going to be very cold, but it is going to lose some heat. So that heat it is going to lose such that it can turn from a gas to a liquid is called latent heat of condensation. You don't need to cram it or dwell about it so much, no. But you should know, like, I have to let you know, because you would be wondering how can it be changing from this to that, no. Just for your own consumption, this is heat lost by a substance to turn from a gas to a liquid. So that happens at the condenser. In fact, that's why it is called the condenser coil. Then there is latent heat of evaporation or latent heat of vaporization. That happens at the evaporator. This is when the substance is going to turn from a liquid to a gas. So at the evaporator, our refrigerant comes in as a liquid and leaves as a gas. So it turns from a liquid to a gas. So what makes it possible is the latent heat of vaporization. You don't need to understand like in detail. Maybe we shall discuss more about it later, but it shouldn't bother you that you need to cram all this. No. Just know there is some kind of heat that is going to sponsor the change of state of that refrigerant as it keeps on changing from one state to another. And that kind of heat allows our rooms to be cold because it is a great amount of heat. For example, I'll give an example of the evaporator. At the evaporator, where we have the latent heat of evaporation, because it is a great amount of heat required to change a substance from liquid to a gas, it will absorb all the heat around as it changes from a liquid to a gas. So by absorbing that heat, as the refrigerant absorbs that heat such that it can turn into a gas, it will pull all the heat in the room and go with it, then evaporate into a gas and proceeds. Then the same thing happens here. As it is going to turn from a gas to a liquid, it will dissipate all. So it will give up all that amount of heat such that it is cold from a gas to a liquid. It will lose a great amount of heat, which is called latent heat. So by pulling a vacuum in a closed system, both the refrigerant, by pulling a vacuum in a closed system before the refrigerant is introduced, this helps lower the boiling point such that the substance can easily change state even at mere room temperature. So when we pull a vacuum, because when you're installing these systems, you will have to pull a vacuum such that there is nothing in the lines to make sure that in these lines, the tubes and the coils and everything in that closed system, there is nothing. There is no air, there is no water, there is nothing. It is a vacuum, total vacuum. So when we pull down to a total vacuum and then introduce a refrigerant into that system, the boiling point of this refrigerant will lower to the extent that even a mere kind of heat, like a warm air in the room, will make it boil. You understand? It will make it boil. The boiling that takes place at the evaporator is not the boiling that you understand, like you're boiling your water at 100 degrees Celsius. No, this is going to be boiling at even mere room temperature. Just 27 degrees Celsius are enough to boil this refrigerant into a gas. Just 27 degrees are enough to boil it up. Then, the next slide. Yeah, next slide is common refrigerants. This blood that is moving around the system, we have different blends, different types of refrigerants. They all have advantages and disadvantages that as we are going to discuss. So I've tried to list a few common, the most common that I've seen in the field, and those that are there, okay. Like I've not seen each and every refrigerant, but the most, like what I've seen most is what I've listed. So there is R410A, you'll find this a lot. Then R22, R404A, R is like refrigerant. And then the figure will indicate the figure will indicate what it is made of, whether it is a single chemical or a mixture of chemicals. For instance, if you see a figure that is 4, starting with 4R4 something, and they are 400 series. They call it 400 series. When you see a figure that is 400 series, that indicates that this refrigerant is a mixture. It has more than one refrigerant. more than one chemical mixed together. Then when you see a figure that has only two, the 22, when you see it only has two, it will be having only one refrigerant. Then when you see refrigerants that have the 700 series, those are natural gases. They are natural, like they occur naturally, like ammonia, like carbon dioxide. Yeah? Those are natural refrigerants. Like water is R718. Yes, that is water. That is the figure for water. So by time, with time you will come to understand, but you don't need to cram the refrigerants you need to understand most are R410A, R22. Those two are the most common refrigerants that you will find in the field. Then the others will come in as you go on, like as you practice more and more, you get to know all of them. But don't cram so much that you need to sit down and like read, like, no, just open up your mind, consume whatever I'm saying, you consume whatever, then what you don't understand, you can please raise it up and then I explain more. Then we have the 200 series. This 200 series, the 200. This will imply that it is a refrigerant that is anyway, R290 is propane. Propane, this is a refrigerant, but it is a gas that you use to cook. The gas, cooking gas, that is propane. But it can also be used as a refrigerant. Then there is R600A, butane. This is what we used in school for those who did some little chemistry, the Bunsen burners. This was the gas that was used in Bunsen burners, butane. Then R134A, you will come across them, but you don't need to cram the figures, as I've said. So as you know, these are chemicals, and chemicals will have an impact in one way or the other. They will have some side effects. So the next page shows us the side effects of these chemicals, and that is the ODP and the GWP. ODP stands for ozone depletion potential, the ability to damage the ozone layer. It usually ranges from 0 to 1. This is how scientists graded refrigerants. They graded them, giving them a figure from 0 to 1. So when a refrigerant has 0 figure, it means that it can't damage the ozone layer. But when it has 1, that means it has a very high potential damaging the ozone layer. And whatever is in between is also not good. So for as long as the refrigerant has a figure, that indicates it can damage. But if it is 0, that is okay. So the closer the refrigerant measures to 1, the more harmful it is to the ozone layer. Refrigerants that contain chlorine, such as Freon or R22, are most likely to contribute to ozone depletion. So R22 is a great enemy of the ozone layer. It contains chlorine. Chlorine damages the ozone layer. The second one is GWP. GWP is global warming potential. I think all of you have been hearing about global warming. Yes, global warming is on the rise. When a refrigerant has a GWP of 0, it indicates that this refrigerant has no global warming potential. But as you scale up and go to over 250, 2,500, that means the refrigerant is very likely to contribute to global warming. So less than 150 would be considered low. Between 150 to 2,500 is medium, and greater than 2,500 would be a high GWP. HCFC or hydrochlorofluorocarbons refrigerants have the highest GWP. So refrigerants that are named as HCFC have a very high GWP rating. Refrigerants with an ODP of 0 would be considered environmentally safe, but not eco-friendly, since they still have potential to contribute to global warming. So if a refrigerant has a 0 ODP, it doesn't indicate that it is a good refrigerant, like it's good, like no, because it might be also posing a threat to the global warming. Or if a refrigerant has a good value in global warming, it doesn't indicate that it has no problem with the ozone layer. So these refrigerants, you always have to look at these two figures as you're picking refrigerant. So I would say that is for the designers of systems, not us technicians. Your job is not to select which refrigerant you're going to use or which one has a great value of EWP or no. That is for the designers. Your job now, the reason as why we are studying this is to understand the implications of these chemicals as you're dealing with them. You're going to be working with them, you're going to be refilling systems, you're going to be collecting these chemicals from units. So you should be vigilant as you're dealing with them, not just dispose them into the environment, not just them under them carelessly, because some of them are very dangerous to the environment and us human beings. The next slide, a table showing ODP and GWP of some refrigerants. Yes. So this is a table that is going to show you how these refrigerants are rated by means of ODP and GWP, where they are applied, and some points to note. So we start with propane. Propane has R290. It has ODP of 0 and a GWP of 6. This is very good in terms of GWP and ODP, but still, this is applied in HVAC and refrigeration, so we use them in both fields. Then the point to note is environmentally friendly, but highly flammable. It can easily catch fire. So it is very good to the environment, but still when you're handling it, in fact, these are one of the most dangerous refrigerants you're going to deal with. They are very flammable, they catch fire easily. So when you're dealing with a system that has propane in it, you have to take extra caution. Then R410A has the ODP of 0, but a 2088 GWP figure. That is high, though it is not in the warning range, but it is still high. It is used for HVAC and refrigeration, operates at very high pressures. So the point to note here with this refrigerant, R410A, is that it is a high pressure refrigerant. It operates at high pressures. Then R404A has 0, then 3,922 is used in refrigeration. Yes, refrigeration only. Though I wouldn't say only, because you find systems that are going to be designed and working in different cases, but it is mostly used for refrigeration. It has a very significant GWP, the 3,900. This is beyond 2,500 we are talking about, that is medium or at least. Then R134A has a ODP of 0 and 1,430. It is used in HVAC, automotive AC and refrigeration. Very good for hot climates with low operating pressures. So this one operates at low pressures compared to R410A. This one operates at low pressures. We shall look at them in the future. Not in the future, even in the next slide, we shall look at the pressures, operating pressures of these refrigerants. Then R22 has a problem. As you can see, it has some figure under ODP. It can damage the ozone layer. So it has a problem. And then when we look at it, DWP is not that bad, but basing on the fact that it has a figure under ODP, it is harmful to the ozone layer. For those of you who don't understand the ozone layer, that is the layer that is protecting the earth from direct sunshine. So as the sun rays come from the sun, they are first blocked by that ozone layer and filtered before they come onto the earth. So by filtering those rays, they don't burn the earth so much to be like some kind of curtain or glass to at least protect the earth from that hot sun. So if we damage that layer, that means we are exposing ourselves to the sun. Of course, we can now see what is happening all over, because the sun is too much now. It is going through the ozone layer like there is nothing. So it is causing a lot of issues. So some of this refrigerant R22 was banned in some countries, and it is now being phased out worldwide. Like in the US, there is no more production of R22. There is no more production of R22. What is there is what is in the units. And when you recover, take it to the facility, they will just recycle, but they will never make new. There is no new refrigerant R22 in the US. For the rest of the world, they are just phasing it out. Some they have downscaled in the production of the refrigerant. Yes, they are downscaling production, and some other countries are following US banning the refrigerant because of its ODP value. Yes. The next one on the list is R12. R12, this one has ODP 1, as we say, ODP 1. This is very, very, very harmful to the ozone layer. And also, the GWP is over 10,000. So this one is, I don't know, menace. I call it menace. This one is a disaster. So this refrigerant was banned in 1996, even before some of you were born. It was banned a long time ago. It is no longer produced nor available on the market. If people have it, they have it on black market. If they are producing it, they are producing it illegally. It is no longer allowed to be produced and used. Then there is R717, that is ammonia. Ammonia, as I said, is a natural gas. As I said, these 700 series indicate in natural refrigerants. So this one is okay to the environment. Very, very okay to the environment. It is eco-friendly, but very toxic to humans. If ammonia is that gas that you smell when you break a rotten egg, that sensation you feel is ammonia. So that's how ammonia smells, and it is very toxic to humans. If you lock up someone in a room and then introduce in ammonia, you will die in minutes. So it is very, very toxic to humans. The last refrigerant we have here is R744, which is carbon dioxide. As I said, seven series are natural refrigerants. So they have no problem with the environment. So the problem with this, point to note, is extremely high operating pressures. This carbon dioxide operates at very high pressures. So it needs very robust systems to handle it. So it is very dangerous in that way. Though it has no problem to the environment, but it is somehow dangerous to humans and very expensive to maintain, to use. It is very dangerous because of its extreme high operating pressures. Our last slide shows the operating pressures of some key refrigerants in the field. So now this one indicates, shows refrigerants and their pressures, operating pressures and standing pressure. First of all, I will define what standing pressure is. Standing pressure, this is the pressure, like this refrigerant is not under any mechanical work, like it is not under any, it is not, how should I phrase it? Standing pressure is, it is not doing anything, like I'll give an example of a system that is off, it is switched off, and there is refrigerant within the coils and the pipes. So if the compressor is not running, there is nothing mechanical happening, the pressure the refrigerant will have inside those systems is a standing pressure. It's like the settling pressure. The same pressure is going to be in the cans carrying this refrigerant. This can, you have this can and you measure, you see at the top here, you have a port where you can measure the pressure, or this is where you will get the refrigerant out. So if you were to put a gauge and measure pressure of this refrigerant, the pressure that you will get is a standing pressure. There is nothing happening, nothing going on, it's just seated there. Then we have suction pressure. The suction pressure, this is the pressure you will measure on the suction side or suction line of the system. The suction line of the system is the line before the compressor. This line before the compressor, the suction line, will have a suction pressure. So if you measure pressure on this line, along this line, from evaporator into the compressor, that is the suction pressure, or low side pressure, or low pressure of the system. It will be on the suction side of the compressor. Then the discharge pressure. Discharge pressure, this is going to be on the discharge of the compressor, on the discharge line of our system. So now image here, this red line, the discharge line. If you measure pressure here, we could measure pressure on this discharge line. Yes, we could measure pressure there, but basing on the fact that it is very hot, it is not really advisable to measure pressure from here. So what we do, we measure pressure from this liquid line, like after the refrigerant has cooled somehow through the condenser. When it goes through the condenser, it will cool somehow. Yes, so if it cools, then the pressure we get on this liquid line is the discharge pressure. We shall see that in detail in future. These are some of the figures of different refrigerants. Like for instance, for R410A, if you measure that can or go to a system that is off, when you put your gauges or when you measure your pressure in that system, you will see around 225 psi. This depends on the temperature around the system also. Yes, so it is not usually, like it is not net that it has to be 250 or 225 psi. No, but it will be close to that. You see maybe 220 psi or 230 psi, that's it. Then we go to suction. The suction or operating pressure, or suction, or the suction operating pressure of the unit that as R410A will be between 110 to 120 psi. It will be between, again, depending on the temperature around the line or around the system. Then we go to the discharge, it's 400 to 450 psi. That is on the high side of the system. So this is on the low side, then this is on the high side of the system. R22 standing pressure will be around 150 psi. Then the operating pressures will be section pressure or low side will be 60 to 70 psi. And then high side or discharge pressure will be 250 to 290 psi. So if you're in the field and maybe you don't know what you have in the system, maybe you have found the system, the documentation of the system are not there. But when you put up your gauges and measure pressure, you see these figures, then you start relating it to this refrigerant. Because you won't tell it is not like color coded that you will see that all the gases coming out is blue or green or what. So it is this refrigerant. You can't tell. You will only tell by means of pressures and temperature. Then also R134A, those are the pressures, the related pressures. Then R32, those are the pressures. Okay, so I talked of R134A being a low pressure refrigerant. As you can see, it has a suction 32 to 40 psi, and then discharge, the high pressure of that refrigerant will read 140 to 180 psi. So this is a very low pressure. And compared, for instance, to this R410A, you see the discharge is over 400, and this one is just 100, below 200.